Okay, it's time to start the next talk. And it was already announced, so please, Professor Petruhanov.
Yeah, hello, ladies and gentlemen. But firstly, I would like to remark that I'm not professor, I'm just PhD student. And
I'm sorry, it's a usual tradition in conferences.
okay.
All speakers will be professors.
Actually, going to the core of it, professor means just a teacher, and originally, and if you are giving a talk, you are teaching at that moment. So at that moment, you are teacher and professor.
Makes
So
sense.
don't worry.
So my talk today, I would like to give a talk that's called optimization of state transfer and exact dynamics for the level open quantum system. So yeah. So we consider the KSL master equation here. Lead control. You can see that we have controls UK in the Hamiltonian. They are called coherent control, and we have control N in the dissipator L calligraphic. So physically, coherent controls can be represented by electromagnetic field, for example, weather pulse, and coherent control can be a spectral density of the environment. For example, if you have, we can have, for example, Planck distribution that is parameterized by the temperature T. So the exact form of the dissipator L can be derived by two different limits that are known in the literature. The first one is weak coupling limit, and the second one is low density limit. Here we consider only weak coupling limit. And our control goal is to optimize some kind of Mayer-type functional that depends only on the final state of the system. And the main kinds of these objectives are maximizing and minimizing observable mean value. So we have traits of the density per rho multiplied by the observable O, and we want to minimize or maximize it. Or also, the objective of state transfer is considered. Here it can be written as just the square of the norm of rho of the final state with some control minus some target state where we want to steer our system to. So we want our system to be in this state. So different numerical optimization methods are used for this kind of control problems. And many of these methods, numerical methods, they use gradients. So it is very important to be able to derive these gradients of these control objectives. And here we discuss the most the simplest case. This is the qubit, open qubit, because we have environment. So I forgot to say why we actually consider the environment because in the real conditions, environment can be isolated and it has its own effects, mostly bad destructive effects on the system. But if we have control, if we can control the environment, we can turn the environment to the positive, as to the positive thing, to use it as an active control of the system, besides our coherent control in the Hamiltonian. So we have this kind of the model for the two-qubit system. We got here control Hamiltonian V, which is actually sigma x Pauli matrix. So this is the rotation in the Bohr ball along the axis x. And for dissipator, we have the form that's given by the coupling limit. Here we have omega, which is transition frequency, mu and gamma. They're just parameters that responsible for the strength of interaction with controls, with control coherent here and with the environment in the dissipator. So due to the low dimensions of the system, it is very convenient to move to the Bohr ball. I guess I should to draw it. I guess everybody knows what is Bohr ball, but so we got so from the space of 2x2 complex 2x2 density matrices, we go to to the ball with the radius 1 in the R3, and this picture will help us later. So we have rotation along x-axis by the coherent control, and yeah. So we in the Bohr characterization we got this different differential equation with control u and this I should note that this system is inhomogeneous because it turns out to be inhomogeneous because of this additional part. And we consider piecewise constant control because it is quite simple to analyze, and it is actually used in different numerical methods. So due to the simplicity of the control, our evolution is quite simple. This is just the sequence of matrix exponentials and also some additional terms. So we got simple derivation. Then to compute gradient, we can use the chain rule. So the last thing is to derive gradient of the final state with respect to the controls u and n, which are, if you use piecewise constant control, it's just vectors in Rm, in the space Rm. So as it is not very hard to derive gradients, we got here derivatives with respect to components of the coherent control and with respect to the incoherent control, but they looks the same, so I don't write them here. Let's move further. So these formulas are quite simple, and it is very interesting. Can we diagonalize matrix exponentials that enter these formulas for the dynamics and also for the gradient? So due to the fact that our system has dimension 3, we can just diagonalize it, because characteristic equation has is third order, has order 3, so we can use Cardano formula. Here we introduce new notation, U hat and hat for convenience. And Cardano formula gives us the roots of characteristic equations. Then we can write eigenvector, and if we have double triple root, we also need to construct a Jordan chain. So we have first and second vectors of this Jordan chain. And the matrix exponential have the known form, has the known form. Then also we need to rigorously analyze some cases when we have double or triple root. So the common case is when we have 3 different eigenvalues. It's simple. Then if we have one double root, and if we have triple root, then controls an unknown. Yeah. Also, we can see here that these formulas are true if denominator here doesn't equal 0, and it turns out that when this denominator 1 plus n plus lambda squared equals 0, it is if and only if coefficient control U equals 0. So also we need to consider this case. Then coefficient control U equals 0, and here we have this kind of this matrix exponential. You can see here that this is rotation. Let's draw it. Rotation in XY plane. This kind of. And along the z-axis, this is dissipation to the center. But if you write, because the system is inhomogeneous, the evolution is the following, and we have here additional part. So actually, it is dissipation to some stationary point that is 0, 0, and 1 divided by 10 plus 1. Yeah, and also we wanted to consider the case when gamma equals 0. This is the case when we completely isolate our system, then the environment doesn't affect the system. Because this case was considered already in the following work here. So we wanted just to compare the results, because this work results was was given by another approach. Does this approach coincides? That was the question. So actually, yeah, it coincides. When gamma equals 0, it is this when new notation in coefficient control n equals 0. And we have the following matrix exponential. And the evolution is matrix exponential multiplied by initial state, and there is no additional term. So this is the rotation along the axis that is this axis here is right. So we have rotation along this axis. It has 0 y coordinate and has non-zero nx and nz. And if let's move to the start. Here, you can see here that Hamiltonian H0 actually is omega divided by 2 sigma z. You can replace it by this Hamiltonian. So this is the rotation along the z-axis, and coefficient control gives us rotation along x-axis because here is sigma x. So if you have 0 coefficient control, is rotation along x-axis. If you have the infinite coefficient control, is rotation along if you have infinite coefficient control, this is rotation along x-axis, and if you have 0 coefficient control, this is rotation along the z-axis. So if you have some non-zero and non-infinite, this is just rotation along some axis in this plane, which has the known coordinates. So that's all I wanted to say. In conclusion, I would say that we considered the open qubit, which is controlled by coherent and incoherent control. We derived expressions for gradient and dynamics, the matrix exponentials, and also we diagonalized these matrix exponentials by Cardano formula. It was possible because of the low dimension, and I would like to add here that if you just move and increase the dimension just a little bit, for example, if you want to consider the system with dimension 3, so we can't do the same because we got the system that has dimension 8, system of differential equations. So it can be the Hertz equation of the 8th order doesn't have the formula for the roots. So this is the only case when this approach can be used, but very important case. So that's all I have to say. Thank you for your attention. If you have any questions, you can ask them.
Thank you very much. Please, questions, remarks, comments? Yes, any questions? No questions. Then let's thank the speaker. Thank you very much.